All right. Well, how's everybody doing today? Feeling all right? Doing okay? Holding up to the weather. People bring out their their big snow boots. It's exciting stuff. This is very strange. Like sometimes, like it's not unheard of to like have a storm early-ish in September, but usually it like will pretend to snow and it'll throw down a little bit, and then it'll be like 70 degrees the next day. This cold snap is weird, but that's all right. It's sort of ease you into this whole Wyoming winter situation. So cool. All right. Good to see you all. My internet connection thus far has been stable, which is a nice thing. I failed in trying to do a live lecture in PSYC today, so hopefully this holds in. I sort of restarted a router and all that stuff, so we'll just cross our fingers. Before we get started in the material today, any questions on our first problem set? So you're going through anything that came up, something you want clarification about or not exactly sure what I'm looking for. Okay, cool. So again, if something does come up, let me know. This first set is relatively less labor intensive than stuff that we'll get into later down the semester, but there's still like some complicated issues with this. So just make sure that you're going through, that you're reading carefully, that you're sort of giving me good answers. Again, you don't have to have pages and pages and pages of stuff, but you want to at least explain your answers so that I know and CJ knows that you know what you're talking about as you're working through stuff. Okay. So we will have this will be due Friday at noon. So make sure that you go through, submit those to CJ, CC me on those. Okay. So for this first set, you'll just have your written responses, and then I've seen a couple of you took snapshots and pasted those in terms of photos, in terms of your hand calculations. That's fantastic. Make sure that you do that. And then the only other thing that we want for these assignments, and this just helps CJ and I move through these a little bit more quickly, is what we want is at the end of your document, just have a separate page that just says appendix, and just any question that asks you for some sort of numerical answer, just put your final answer in there. Okay. That way, what we can do is we can go down through. CJ can go through and say, okay, for number 2, let me see. First one, you need a. So it looks like for numerical answers in this set, 4, 5, 6, 7, 8, 9, 11, and 13 all have some sort of numerical response. Just go down through and say 4, and then write whatever numerical answers you need to have for that. That's just a way that we can go through and just check the boxes, make sure that if those are good, then we're good to go. It just speeds up the process, helps organize things a little bit, so we don't have to hunt through sort of large amounts of text to try and figure out where the response is. Okay? Does that make some sense to everybody? Okay, cool. And this will be quick and easy to run through and do. It shouldn't add any extra time in the prep for this. All right, cool. So let's go through and pick back up where we left off last time, talking about z-scores, standardized scores. Any questions on anything that we covered up to this point in terms of thinking about how we're thinking about conceptualizing standardized scores? Feeling comfortable with this?
Can I ask you one question real quick, though?
Yeah.
It's kind of like a clarification thing. It's me not clarifying myself. I wrote variability goes down, test statistic goes up. Is that right? Is that even something you said?
Okay. Yeah. So someone help us out. Someone help us out. Why I did say that, and sort of looking at information on this slide, why would I say that? Why does this make sense?
Oh, well, I guess, like that, as well, someone else. So I mean, I understand what I wrote, but I don't quite understand what I wrote, if that makes sense. So, like, as variability goes down, your test statistic goes up. So I guess, like, the less variable things are. I don't know. I can't.
No, keep going, Brittany. So don't give up. So why does this make sense? If we look at your formula for your z-score, why does this make sense?
Well, as your is test stat the law score?
Nope. Test stats not your, which of these which of these things is your test score?
Your Z score.
Yep. So in this case, it's going to be your z-score.
Oh, so as variability goes down, oh, okay, well, it makes sense to me now, because, like, if it's less variable, then your test statistic is going to go up, which means that, like, they're farther from the mean, if that makes sense.
Well,
I think I'm confusing myself.
okay. So, Brittany, what is this right here? X.
That's your observed score.
Yep.
Yeah.
And what about mu here?
That's obviously your mean.
Okay. And sigma here?
Yeah, standard deviation.
Okay. And z is your test score, right?
Mm-hmm.
So if my standard deviation or my variability gets smaller, did my score get farther from the mean? No, score is still the same difference from the mean, right? But if my variability gets smaller, it means that the average degree at which people deviate from the mean starts to get smaller, right? And so mathematically, if we hold everything in the numerator constant and start decreasing this, what does that do to my z-score?
If you hold everything, you decrease your standard deviation?
Yep.
Well, then your z-score goes up, right?
Yep. Okay. And this is just, I'm glad you brought this up, because this is as we go through, we're talking about T statistics and F statistics and everything else, right? Almost for the stuff that we're doing this semester, the denominator of these test ratios is going to involve some indication of, or be influenced by your variability, right? But for our means-based tests, that variability shrinks, right? As our folks get less and less variable around our mean, as we start to get less error, right? Our t-scores start to go up, right? This will be the same thing for our effect sizes, for our t-tests, for everything else, right? And so this is why, as you're working through this, don't ignore the formulas, because one, you'll need to use the formulas, but one, if I take a look at this, I'm saying my standardized score is a function of the deviation from the sample or the distribution mean over the variability. So my variability shrinks if everything else stays the same. My z-score goes up, right? Holding everything else equal, as my distance from the mean increases, my z-score goes up. My variability increases, my z-score goes down, right? So if we're thinking about, let's say, someone in my Gen Psych class is 25 years old, okay? How much variability is there likely in my Gen Psych class?
Well, there's probably
in terms of age?
Not much, besides the 25-year-old, right? Because they're most like 18 or 19 years old.
Right, probably, right? And so they're going to have some variability. But, so the z-score for that 25-year-old might be quite large. What if I went through and I put this person and referenced them to the average age of all students on campus? Is their z-score going to get bigger or smaller?
Smaller.
It's smaller, right?
Closer to the, okay.
Exactly, right? So just wanting to think about this in conceptual terms will help a whole lot, as opposed to just trying to plug things into formulas. Okay, cool. Anybody else have questions with this? Thank you, Brittany. That's helpful. I, again, can't emphasize enough how important it is to have a strong understanding of this stuff.
Okay.
Cool. All right. So, again, for this example, what we're going to be doing a lot today, this is super helpful to go through and plot out the examples that we're using today are going to be assuming sort of normal distribution. Here we have our z-scores. Here we have our raw scores. And what I can do is, if I know the mean and the standard deviation of a distribution, if you give me a raw score, I can calculate a z-score and then start to infer something about how common or uncommon a given observation might be. Okay. So, what we can also do with our z-score formula here, we can start to go through and manipulate this z-score so that I can start to solve for other values if I start to have enough information available to me here. Okay. So, for example, if I say I've got a z-score of 1.96 and I have a distribution mean of 73.6 and a standard deviation of 14.8, okay? What I can do with a little, and you're going to exercise a little bit of, a little bit of algebra here that you maybe have forgotten. So I've got a, let's see if this works. So I've got, Z 1.96. I've got mean equals 73.6, and I've got standard deviation 14.8. Okay, so I know I've got 1.96 is equal to x, that's what I don't know, minus 73.6 over 14.8. Okay, how long has it been since people have done this type of stuff? Maybe a while, right? Okay, what we need to do is we want to solve for x here, right? That's what we want to know, right? So if we go through, multiply both sides by 14.8, right? We're going to end up with 29.01 equals x minus 73.6, right? Add 73.6 plus 73.6. What I'm going to end up with is an x value of equal to 102.61. Okay, and so this right here, right, what I want to know is what's the raw score for a standardized score of 1.69. If my population mean is 73.6, my standard deviation is 14.8. What I can do is I can work backwards and get my raw score. Okay, Ali does, and this is what I talked about this before. Given what we know about z-scores, does my answer make sense given the information that I have here? Yeah. Do I have a positive or a negative z-score? It's positive, right? And so is my value that I got for x, is it above my average? Yep. Okay, so I'm going in the right direction, so that's good, right? I've got a z-score of about 2, right? So whatever I get should be about 2 standard deviations above my mean. If I say my standard deviation is, let's say, call it 15, 30 points above my mean, okay, looks like all of this is coming together, right? So always, it's easy to make mistakes with this. You always want to go through and do a plausibility check, say, does this answer make sense given what I'm doing here? Yeah. So here, let's do another one. And say, if I've got a population with a mean of 65, a observed score of 59, corresponding to z-score -2, want to know what my standard deviation is, right? So here, I'm going to go, I've got a z-score of -2, going to be equal to, I've got an observed score of 59, population mean of 65, and what I want to know is I want to know what that sigma is. I need to know what my standard deviation is. Okay, so again, you're going to do some algebra, multiply both sides by sigma. Okay, that's going to cancel out there. So I'm going to have -2 sigma equals, -6, right? If I divide this by -2, that by -2, sigma equals 3. Okay. Now, Robert, let's say I forgot to carry that negative out and I got a sigma of -3. Does that make sense? Why not?
Because it wouldn't. I guess I'm. Is like it wouldn't be right.
Yeah. So it wouldn't be right. What if I tell you that I ran some analyses and I've got my standard deviation is negative 5.5? What's wrong with that?
Well, there aren't. Well, there aren't really negative standard deviations, right?
Yeah,
Just zero
I,
standard deviation.
yeah. I can have zero variability in my data, meaning that all scores are the same, but I can't have a negative value, right? There's no such thing as negative variability, at least to my, unless we get into some weird theoretical statistics or something. I can't have negative variability. I've got to limit it to zero, right? So again, sort of just recognizing and sort of understanding this stuff will help you from going through and making errors like this. Same thing, population with a standard deviation of 4, observed score 33 corresponds to a z-score 1.5. Same type of thing. We would go through the same process. Would anyone like me to work through this, or do people got a kind of a handle on what we're doing with this stuff? Feeling all right? Okay, cool. So again, this might seem a little bit elementary, but being able to flexibly and algebraically move back and forth between statistics, because what's going to happen over the course of your career, you're going to read papers and people aren't going to give you the stuff that you're wanting to know, right? Maybe someone didn't report means and standard deviations, or maybe they didn't report standard deviation, but they gave you a mean of their sample, and an observed score, and you can calculate and they give you, like, say, an effect size or something like that. I can start to work backwards with the information I have and start to pull things and derive statistics that I wouldn't otherwise have if they're not reported. Okay, so just wanting to be comfortable manipulating these equations to go through and get the stuff that you're interested in getting in published research. Okay, so talking about sort of the benefit of z-scores. Again, our z-scores are going to give us an exact location of some of some observed value in a larger distribution. And what we can do is we can start to take, if the scores form a standard distribution, what we can do is or some sort of known distribution, we can start to compare other distributions regardless of what the mean and standard deviation of those other scales might be. Okay, so for an example, let's take a hypothetical here. So I've got Henry, hypothetical Henry. I like that hypothetical. I'm going to get a T-shirt that just says hypothetical Henry. Don't steal that. That was a good idea. Henry's participating in a study on personality. Okay, scores an 87 on a measure of conscientiousness, 73 on a measure of extroversion. Rachel, which of these personality traits is more prominent in hypothetical Henry? Okay, maybe. Why?
It depends. You don't really know if the scores match up, but
perfect, because we don't know, right? Maybe these are different scales. Maybe these are different. Like, I don't know which one of these is more characteristic of Henry, right? But if we assume that personality exists on a relatively normal curve, and I start to know the mean and standard deviation of these distributions, now all of a sudden it starts to tell me, I can start to get a sense for which one of these is more prominent, right? Same thing, so slightly different based on some stuff that I actually done. So we've got Claire interested in creating a composite quality of life variable based on scores from 3 different measures. Okay, so Claire has 3 different scales that are kind of getting at some quality of life. What she wants to do is combine them all. Erica, what would be the problem of just adding up all the scores on her 3 measures of quality of life and just using that?
The measurement tool, like if it's tested, if each measurement tool is tested in itself, you can't necessarily cross them into one.
Yeah, well, that's brilliant. That's that's a bigger psychometric issue with sort of saying, okay, these are all part and parcel of the same thing, right? But let's say I've got one scale that runs on a 0 to 100 scale and another scale that runs on a 0 to 1 scale because it's like a proportion or something like that. What happens if I start adding those things together?
Depending on, like, if you get a really high score, you don't know what's contributing to that.
Exactly, right? If I start adding fractions to my 0 to 100 scale, I might as well not even add those on because they're not comparable. So let's say let's say it was methodologically reasonable to combine these scales into a common, like an aggregate metric. How might I do that even if they have very, very different scales? Each of my 3 measures.
I don't know.
Anybody help her out?
Could you repeat the question?
Yeah, so I've got 3 different scales, all on different metrics. And what I want to do is I want to combine these up so that to get like an aggregate scale. But they're different scales, they're different sort of metrics. How might I use standardized scores to create a reasonable composite?
Couldn't you convert them all to a z-score, because then you just know it's not about like which mean, it's just that certain mean, they're this far from it.
Exactly, right? So let's say I've got a really high score on my 0 to 100 or my 0 to 1 scale, right? But I have on that scale, I've got a z-score relative to the rest of the distribution. I've got a z-score of 2, right? But that z-score of 2 corresponds to an actual observed score of, 0.6, right? But on my 0 to 100 score, I still have a score about 2 standard deviations above the mean, but that's at a score of 80, right? I can't add 80 and 0.6, that's not going to do anything. But if I have a z-score of 2 on one and a z-score of 2 on the other and a z-score of 1.7 on the third, if I add those up, then that's starting to get sort of rank and file up, right? So this would be just a way we can start to use z-scores creatively as long as we understand what's going on and relationships across things. Does that make sense to people? Why? And as Erica noted, it's probably not the best and most psychometrically sound way to go about these. There's other ways to do it, but just for a quick and dirty approach, this could be something that you could do. Okay. All right. So we want to talk about, up to this point, we've talked about z-scores as following a nice symmetrical normal bell-shaped curve. Okay. But it's important to recognize that if we go through and we take a set of scores, transform those into z-scores themselves don't imply a normal distribution, okay, in the sample or the corresponding population. I can take any distribution, transform everything into z-scores. What it's going to do is it's going to mean that the mean of that z-score distribution, the new mean in my distribution will always be 0, and the standard deviation will always be 1. But the shape of my distribution of z-scores is going to be identical to the distribution of my raw scores, okay? So we can go through and we can transform anything into a standardized score. And if we assume the underlying distribution is approximately normal, we can start to glean some stuff on how likely or unlikely a certain observed score is. But for my set, the data that I actually have, transforming things into z-scores doesn't mean that I'm turning that into a normal variable. My distribution of my z-scores is going to look exactly the same as my distribution of raw scores. Okay, but what it's going to do is it's going to give me my raw scores a standardized distribution. All that means is just that my standardized distribution has some set mean value and some set standard deviation that I've determined just because it's useful for whatever it is that I'm doing. Okay, does that make some sense? Can people see the issue here? Because sometimes you say, oh, they're z-scores, they're normal. That's not the case. We can turn anything into z-scores or any type of standardized score. It doesn't change the shape of the data that we're actually looking at. Okay. So, for example, let's say I've got a set of raw scores here. 0, 6, 5, 2, 3, and 2. In this distribution has a mean of 3, standard deviation of 2. Okay. So I know my first score of 0 is going to be a standard deviation a half below the mean. Give me a z-score of 1.56. It's going to be 1.5 standard deviations above the mean. Z-score is 1.5. My standard or my observed score of 5, that's 1 standard deviation above the mean. Z-score 1. Same thing, negative 0.5. 3, this is equal to the mean, so I've got a z-score of 0. Score of 2, that's a half a standard deviation below the mean. It's going to give me a z-score of negative 0.5. Okay, so what I've got now is I've got my original data, my original scores, and then I've got my z-scores. My z-scores, the only thing anytime you look at a z-score, you should immediately think about this z-scores as distance from the mean in standard deviation units. This is going to be huge, huge, huge help when we start getting into effect sizes. All this is telling me how far that particular observation is from the mean in standard deviation units. But if I go through and I take a look at my histogram of these scores, here's a histogram of my raw scores. Here's the histogram of my z-scores. Ari, how are these graphs? Are they comparable or not comparable? In terms of shape.
Okay. They're both they look like they'd be a little bit positively skewed.
Oh, okay. Yep. So sort of a little bit and it's hard with only just a handful of scores to kind of get a good sense of the shape of the distribution. Are these two distributions similar or unsimilar to one another?
Not similar.
They're in terms of shape.
Oh yeah.
Yeah. They're the exact same thing, right? Like all we did with our raw scores here is we've got our raw scores. We translated everything to z-scores. When we did that, it didn't change the shape of our distribution. Distribution is the exact same, right? And so just really trying to hit this home, we can go through and create z-scores and take a look at z-scores. Z-scores are nice because they give us a position of the observed score in standard deviation units from the mean. Above or below kind of tells us how far, and if we're assuming things are fall on a normal distribution, kind of gives us an idea of like how extreme or not extreme they are, but it doesn't change the shape of the distribution. We're not transforming our data into normal data just because we're creating standardized scores with things. Okay. So we've been talking to this point about z-scores, right? Z-scores, though, are just one example of any type of standard deviation or standardized distribution that we could put together. For anybody doing like personality tests or sort of other type of cognitive achievement tests, we'll see T-scores used a lot. T-score is just a standardized score, but T-scores have a mean of 50, standard deviation of 10. What's the mean of standard deviation of z-scores? Right? 0 and 1. I can take z-scores, I can turn them into t-scores. Now I have t-scores. Only thing that makes them t-scores is that I've set the mean to be 50, standard deviation to be 10. Same thing, IQ scores have a mean of 100, standard deviation of 15. Right? There's nothing unique about that other than I just decided that I wanted the mean to be 100 with the standard deviation to be 15. Same thing, SAT scores. Mean of SAT is 500, standard deviation is 100. These are all examples of standardized scores. Only thing that makes them different than z-scores is if we've just chosen a different mean and standard deviation with this. Okay, and so what we do is we can then if we want to get scores into a certain distribution, what we can do is we can take our raw scores, transform those into z-scores, and then take our z-scores and take those and sort of move those into whatever I want my new standardized score to be in terms of means and standard deviations. Right? So for example, here I've got a set of exam scores that I want to have standardized so that it has a mean of 500 and a standard deviation of 100. Okay, so this would be, let's say, SAT scores. In my raw exam scores, it has a mean of 57, standard deviation of 14. Okay, and what I want to do is I want to calculate my standardized scores based on sort of these observed scores I have here. Okay. So all we're going to do is, once again, here's my raw score. And my distribution has a mean of 57, a standard deviation of 14. First thing I'm going to do is I'm going to calculate a z-score. So 64 is about a half standard deviation above the mean. It's going to give me a z-score of 0.5, right? So Allie, if I've got a z-score of 0.5, where does that tell me the position of this score is relative to the mean? Half standard deviation above. So I want my distribution to have a standardized score of mean of 500, standard deviation of 100. If I know this score falls a half standard deviation above the mean, I just add a half standard deviation to 500, gives me a standardized score in my new scale of 550. Same thing, 43, I've got a standard deviation below the mean, right? Gives me a z-score of -1. To transfer it over to my new standardized distribution, I just take a standard deviation off of my mean, gives me a score of 400 here. Same thing, 57, equal to the mean. I'm 0 standard deviations from the mean right there, so my new standardized score is 500, 71 standard deviation above. Add a standard deviation here, get it, now I'm back to 600. Okay, so again, depending on what types of scales and what types of metrics you use, and you may run into in your research some sort of scales that have normed or been normed and used to calculate t-scores or other types of standardized scores. Don't get intimidated. It's easy to go back and forth between this. We just take the raw scores. If we know the properties of the distribution, just create z-scores and then take those z-scores and transfer them over to whatever metric you want or choose. Questions on what we did here, or sort of how this is working? We're going back and forth with stuff.
Yeah. Yes. Sorry, y'all. So just so I understand it, and I guess someone else has this question too. So you just kind of like set the mean and so the mean to be like 500 and the standard deviation to be 100, and that's how you got this like the standards thing. So you were like, okay, this is above the mean, half the standard deviation. If my standard deviation is 100, then it makes it 550. Am I understanding that right?
Exactly. And Brittany, is there anything special about 500 and 100 here?
The only thing special I know about it is that you said it was SAT scores on the previous slide.
Yeah.
There's nothing to me that.
Yep. There's no. These values are arbitrary. If I wanted, let's say I wanted a sort of the mean of my new standardized distribution to be 65 and the standard deviation to be 3, fine, whatever, I can do that too, right? There's nothing unique or special about this other than for one reason or another, we just decided as we're going through and want to communicate this, we want to have a mean of 500, standard deviation of 100, and that's just what we decided, okay? So this piece is completely arbitrary. Okay. Other questions on this? Okay, cool. So again, when you're going through and doing these types of tasks, again, it's always nice to kind of just draw out your normal curve here. Here's my raw scores, have a mean of 57, standard deviation of 14. That's my actual observed scores. This is what I'm seeing in my observed measurement, but I want a standardized scale with a mean of 500 and a standard deviation of 100. So what I can do is I can, if I'm assuming that these fall on a normal curve, draw my normal curve. Here's my z-score. Here's my raw score. Here's 57, 500. Standard deviation below. So 57 minus 14 is 43, right? 100 minus 500 is 400. Can kind of line these out. And then what I can do is I can just start placing my different scores and seeing where those all put together. For problem set 2, I'm going to ask you all to do a little bit of this just because it's going to be helpful in sort of keeping things straight in your mind so that everything kind of comes together. Okay. Questions on sort of what we're doing here, why this works, anything along those lines? Okay. Cool. So why is this all important, right? This is just fun sort of number of games to play. What are we actually trying to go through and do with these standardized distributions? Okay. This standardization, again, as I've said before, starts to allow us to compare the position rank of different scores irrespective of the characteristics of the distribution, right? So I've got so I run a study on self-handicapping. Allie runs a study on self-handicapping. We both get slightly different samples with slightly different scores. If we should go through, I've got a score of, say, 56, and Allie's got a score of 49. Does my score trump her score? I don't know. It just kind of depends on the distribution, right? If we go through and standardize, it allows us to go through and start to compare things, okay? And in situations where we have scores that start to follow some sort of known distribution, what we can start to do is start to identify the probability of randomly selecting a score of a certain level or above, okay? Remember, if we have something here that follows a normal distribution, there's lots of stuff that in theory in the population we're assuming follows some sort of normal distribution, let's say IQ. What we know is that certain cutoffs in this normal distribution are associated with certain probabilities. And so if you say, what's the likelihood of identifying someone if we're saying, let's say IQ has a mean of 100, standard deviation of 10. If you say, what's the likelihood of randomly selecting someone from the population with an IQ score of 130 or above, if I'm assuming a normal distribution, I can start to add very, very precise estimates of the likelihood of randomly drawing someone having scores with that properties or above, or things along these lines. Okay. And so anybody show of hands, or sort of give me a thumbs up, I guess, in your little thing. Anybody take calculus? Some calculus. Riley kind of took calculus. What about Calc 2? Anybody take Calc 2? No Calc 2s. Rachel took Calc 2. Okay. Rachel can tell you, and you ask her about it. She'll tell you all about it. Yeah, you will. I'm sure that you're not going to withhold information from your classmates. That'd be a rotten thing to do. Calc 2 is about finding areas under the curve, right? So you're assuming certain curves, you're doing integrals. The nice thing about the stuff that we're going to be doing in statistics, no one asks you to do Calc 2. It's all kind of tabled up for you. But what we know is that these frequency distributions are directly associated with probabilities. Okay, and certain areas under a distribution graph start to correspond to certain proportions of the population. And because proportions and probabilities are equivalent, they're just sort of presented differently, what we can do is we can start to use and represent different areas underneath a graph or a curve and start to calculate percentages or probabilities of identifying certain scores here. Okay. So let's say here for this example, we've got a population of scores. So these are all the scores in the universe. These 10 scores that we have here. Okay. My scores are 1, 1, 2, 3, 3, 4, 4, 4, 5, 6. Okay. If I go through and I plot this out in a histogram, right? And I want to know what's the probability of randomly selecting a score greater than 4. I can write this as probability of x greater than 4. Rachel, help me out. What's the probability in this set of getting a score that's greater than 4? 20%. 20%. Did you use Calc 2 to figure that out?
No.
What did you do?
I did 2 over 10.
Yeah.
There's 2 scores.
Yep, exactly. And this is a very simple example of how this works, but in theory, we're doing the same thing with our normal curves, right? So here we have 10 scores. Of those 10 scores, 2 of those scores are greater than 4. 2 over 10 is 1/5, which is 20%. So there's a 20% chance of me randomly selecting a score that's greater than 4 in this distribution. Okay, and so what we've done is we've taken this histogram or this frequency distribution and used that in a way to go through and visualize how we're the probability of obtaining a score of a certain value or above. People see questions on what the magic Rachel worked right there with that? Okay, so what we can do then, if we take that same basic principle, we can start to take this same basic principle and transfer this over into other known distributions. Okay, so if we take a normal distribution, normal curve is a frequency distribution we see a lot in a lot of naturally occurring phenomena, right? So let's say height, weight, IQ, intelligence, sort of lots of things sort of falling on this normal curve, right? And our normal curve is symmetrical. Brittany, what does it mean when I have a distribution that's symmetrical?
It's even on both sides.
It's even on both sides. I cut it down the middle, it's identical on both sides. My normal curve is symmetrical. Highest frequencies occur in the middle of the distribution. As I start to go out to the end, things kind of taper off. And in a normal distribution, my mean, my median, and my mode are all identical, all the same value here. Okay? And what we know is that certain areas under that normal curve correspond to known very specific probabilities. Okay? And so what we can do is we can start to use z-scores as standard units for marking certain areas or probabilities under the curve that we can start to use to infer information about the likelihood of obtaining scores of that area or between areas, things along these lines. Okay. So again, here I've got a distribution with known qualities. 2 of my 10 blocks are greater than 4, so I have a probability of obtaining a score that's greater than 4 in this distribution of 20%. Okay, I do that same thing. If I know something follows, some scores follows a normal distribution in the population, here I've got something that follows a normal distribution. I know that this distribution has a mean of 34.2, and I know that it has a z-score, or excuse me, a standard deviation of 6.8. What I can do is I can start to determine the probability of finding some value that's less than 45 based on this information here. Okay. And I guess let's say we're talking about introversion, for example, here. So what we know with our normal distribution is our normal distribution, again, if we're thinking a mean of 0, standard deviation of 1 for normal z-score, I know that about 68, a little over 2/3 of my scores in a normal distribution are going to fall between -1 and 1. Okay, so if you ask me, sort of what's the likelihood of in IQ obtaining a score, randomly selecting a person with a score of 75 to 115, I'm going to say it's 68.26%. Right? If we go 2 standard deviations, right? Again, if we're thinking about a IQ where we've got, again, mean 100, standard deviation 15, what's the likelihood of getting someone, 85, math did wrong, 85 to 115. If I do 2 standard deviations, if we go 70 to 130, I'm going to know 95% of the population is going to fall between those values, right? If we start to go beyond, it starts to get less and less likely, okay? This is known properties, and this is why if we can assume something follows a normal distribution, very powerful, because what we can start to do is infer certain probabilities of obtaining certain scores and then talk about whether or not this is a rare event or a not rare event. Okay. This here is the formula for normal curve. You don't necessarily need to know that. But what happens, Robert, if my distribution doesn't follow this formula, right? If it's different than normal, right? Can I still use these same probabilities to infer likelihood of obtaining a score? No, I can't, right? Because it's a different distribution. It's not the distribution that I find, or that I'm assuming, or that's assumed with sort of this set of numbers, Robert, do you know what we call a distribution that deviates from normality? My students laughed. They know where their bread's buttered. All right. People understand kind of how we're using these distribute. Eric is trying not to laugh. I say you can't cover your mouth. Try not to laugh. I see it in your eyes, right? All right. Questions on the normal distribution, how we're trying to use, and how we're going to go through use this to start making inferences about the likelihood of certain scores. Okay, cool. So let's give this a try. I've got a population of adults normally distributed with a mean 68, standard deviation of 6. Okay. Given properties of normal distribution, what's the probability of randomly selecting an individual at or taller than 80 inches? All right. Ari, just knowing what you know about humans, is it likely for me to randomly get somebody who is 6'8" or taller? No, right? And so as I'm going through and doing this, whatever score or answer I get, I should sort of recognize that that's going to be pretty narrow, right? So what I'm asking here is, what's the probability of getting an X value or a randomly the height of a randomly drawn person that's greater than 80 inches? Yeah. So what I'm going to do is I'm going to first sketch out sort of my normal distribution, because I'm assuming normal distribution for height. Okay, I know that I have a mean of 68, standard deviation of 6 inches, right? So here's 6 inches. Here's 74. 80 is out here, so I'm going to make that and then kind of shade this in. Okay, so this is the portion of the distribution that I'm looking for. Ari said that this is, I'm unlikely to get a randomly selected person who's 6'8" or taller, and so we should expect this part of the part of the tail of the distribution to be pretty minimal, right? What I then do is I can identify the exact location of this score of 80 by calculating my z-score. We know that a score of 80, if we go through and calculate a z-score for 80, I'm going to get a z-score of 2, right? So if I take 80 minus 68 divided by 6, I'm going to get a z-score of 2 here. Okay. And then what I can do is I can determine the probability associated with that area of interest. So a z-score greater than 2 using my unit normal table. Okay, so this is where I said have that z-score table up and ready to go. This is an example of my unit normal table here. So this is my z-score table. Z-score table that I sent you has a number of different columns. So here we have a z-score, right? This is our z-score. These tables are actually kind of slick. We'll tell you the probability of obtaining a score between the mean to wherever your z-score is. Larger portion, if this is my z-score, it's the big, anything to the left or right of that. Smaller portion is whatever's in the tail, and then you can ignore this y column here. Okay. So going back, if I've got a z-score of 2 that corresponds to someone who's 80 inches tall, if I go through on my unit normal table, Riley, help me out here. What do I need to find in this unit normal in my z-score table here?
Wouldn't you want to look for a z-score of 2?
Yep. I'm going to go down through and I'm going to look at a z-score of 2. Okay. And here it is. Found a z-score of 2. And if my question is, what's the likelihood of obtaining someone at or taller than 80 inches? Which of these scores am I going to be looking, or which of these columns am I going to be pulling from? The smaller portion, right? Because if I go back through, it looks like I'm looking at the tail here, right? And again, bring it home, Riley. What is the likelihood of me, if I'm going through and just randomly selecting in the United States, I get sort of census data and pull someone randomly from there, what's the likelihood that that person is going to be 6'8" or taller? Yeah. So about 2.3% chance, right, that I'm going to go through and pull someone who's 6'8" or taller, right? And all I needed to know in order to get that information is I needed to know the population mean, population standard deviation, and then once I have that, I can start to get very, very, very specific probabilities, assuming that my distribution of whatever I'm looking at is normal. Okay. So this is probably okay, let's do this real quick. So assuming, so pull up, you have your z-score tables up here. Assuming that we have a normal distribution, what's the probability of selecting a z-score at or greater than 1? Someone jump in with this.
15.8% or 15.9%.
15.9%. Yeah, Natalie. And so what Natalie did is we're looking for a score that is greater than 1. So Natalie went through, found a score of 1. What we're looking greater than 1. So we're looking at something in the tail. And so right here, we've got about 15.9% likelihood of finding something, assuming a normal curve, obtaining a score with a z-score of 1 or higher. Okay. What about assuming normal distribution, probability selecting a z-score at or less than 1.5? Someone brave who's not Natalie.
I have a question, so I guess I'll answer it too. Is it 0.9332?
Okay.
About 93%.
Okay. Yes.
Okay.
Okay. How do you get that, Brittany?
I looked at, and this is kind of like my question. I want to ask if it's like an all the time case.
Uh-huh.
I just went to the 1.5, and then because it says, and this is my question, if it says less than, is it always the larger portion?
No. No.
Okay, so like I chose so then I guess I chose larger portion because I got lucky because like I mean, you know what I mean? Like I thought, so how do you know to choose between larger portion and smaller portion?
Okay. Yeah, that's a good question. And that's where this starts to come into play, right? So I go through, and here's my normal curve, right? And I'm saying this is 0, right? Whoops. And what score am I looking at?
The one that's less than 150?
Yeah, right. 1.5, right? And I'm wanting a score that's less than 1.5. So I'm talking about all this piece here. Okay?
That makes sense.
You know? Now, if I was going through and wanting to say if the question was, what's less than 1.5? Now which portion am I looking at, Brittany?
What's like, the stuff in between?
No. Let's say, all right. Now let's say instead of 1.5, I want to know scores that are less than negative 1.5. What portion of the table am I looking at now?
The smaller portion.
That's going to be the smaller portion, right?
Okay.
That's going to be all this stuff, right? And so this is where plotting this out starts to become helpful.
Yeah.
And so yes, for 1.5, your probability of obtaining a score that's less than 1.5 standard deviation units above the mean of a normal curve is almost pretty certain, right? 93.3%. Okay. What about, Robert, help me out with this one. Assuming a normal distribution, what proportion of the normal distribution is contained below negative 0.05?
That'd be 31%.
About what?
31%
About 31%, right? So again, if I go to, remember that this is symmetrical. There's no negative values on your Z table. But if I go to 0.5, right, and I know that I'm less than 0.5. So again, let me see here. This time I'm looking at negative 0.5 is maybe say about right here, right? I'm looking at this stuff, right? So should my value be greater than or less than 0.5? It'd be less than 0.5, right? Because I'm getting less than half the distribution here, right? And if we go to my z-score or my unit normal table, I see that the likelihood of obtaining the score less than negative 0.5 is going to be about 30.9% or about 31%. Okay. So this is just going through and finding and identifying sort of different sections of this unit normal table. Okay. Questions about what we've done here? Okay. Let's okay, yeah. Let's run through this quick, and then I'll let you turn you loose on a break. If once again, we're going to change things around a little bit. If I've got a normal distribution, right, what I want to know now is what z-score separates the top 10% from the rest of the distribution. Erica, can you help me out with this one? So I'm looking for the z-score that cuts off the top 10% of my normal distribution. So what column am I going to be looking at here? The smaller portion, right? And so if I go down that smaller portion, and if I go through and this one's probably closer, right? So this is going to say the top 10% is going to fall above a score of 1.28. So what I would say is that, again, if I go back to my drawing here, oops, put it down here. This 1.28, about 10% of the distribution is going to fall above there. Okay. What about how about this, Allie? What z-scores form the boundary that separate the middle 60% of the distribution?
Would it be like 0.85 and negative 0.85?
Yeah. I got about 0.84 plus or minus, right? But if we're thinking about the middle of the distribution, right, we're wanting something that's, here's my distribution, here's the middle. I'm wanting here, here, and what am I looking for? Middle 60%. That's maybe a little bit not. Should have those out a little bit maybe. But what I want is the stuff in the middle here. Because I know this distribution is symmetrical, what this is going to give me is something about negative 0.84, 85. It kind of falls in the middle to 0.84, 85 here in the positive. And again, if I go through and say from my mean to z, I'm looking for about 30% here. It falls kind of right there in the middle of that, about that, right? And so somewhere between plus or minus 0.84 or 0.85 is going to capture the middle of that distribution for me. Okay. People see how we're sort of using this to start to find different proportions of the curve and different probabilities and things like that. So again, it seems kind of silly to be drawing pictures, but trust me, this is very, very, very helpful to keep this clear in your head. I went through and solved all these before I got on with you and screwed 3 of them up because it's easy to do. So trust me, having this type of thing, and I'll ask you to sort of graph some of these out in your next set. This is a helpful thing to go through and do. Okay, cool. All right, so let's do this. Let's go. Let's take a break. Be back at 3:20, and we'll jump back into material here once you get back. Okay. All right, folks. Questions about anything that we've covered up to this point.
I'll ask. You may ask my question.
Okay, yeah. Ask your question.
How did God, I feel so. How did Allie know that these Z-scores form the boundaries? Like, what did you look at?
Mm-hmm.
How did you know that that was the 60% that was in between that number? Because when I look at it, I'm like, okay, 0.84 says 30% on the on the larger portion it says 80% and 20%. Does that you just look at that 60% right there is what makes that boundary right there?
Go ahead and take it, Allie. How did you figure that out? What column were you looking at when you solved that problem?
Yeah, so I just looked to the mean to z column because that would be like halfway between. So if it's like 60% in the boundaries, so you want to see so the mean would split that in half, right? So you're looking for like 30% on either side of the mean.
Oh, okay. That makes sense.
Got it?
Okay.
And this is a pretty slick feature of this unit normal table, is it'll tell you middle of to wherever the sort of midline of the score is. Sometimes they won't, so you have to do some additional subtraction and stuff like that. Okay, cool. Any other questions with some of the calculations that we were doing? Okay, a lot of this is kind of review of basic undergrad statistic classes and things, but again, having a good understanding of this and being able to work flexibly with it is going to help as we sort of start to move forward into more complex analyses and interpretations and things. So, all right, I will share screen, get back here. Okay, so as we start to do some more involved types of complications, or sort of more involved types of calculations, keep in mind that we have a direct relation between raw scores and z-scores, and then proportions, probabilities, things along these lines. I can take raw scores, turn them into z-scores, go back and forth. I can take z-scores, turn them into probabilities, back and forth. But to attach probabilities to raw scores or raw scores from probabilities, I'm going to have to do some intermediate calculation of z-scores in order to go through and get that information. Okay. So if I want to start to attach probabilities to specific x values, and this is where we're going to be sort of most likely case, what I'm going to be interested is selecting a score, interested in the probability of selecting a score at or above a certain sort of x value, right? So again, Erica, let's say that you're working on, say, personality or something like that. And I say, oh, hey, I'm excited about, I want to find a z-score that's above, or the probability of finding a z-score on this measure that's above 1.28. Well, a z-score of 1.28 on that measure, I don't know what that means. I don't sort of understand that, right? What's more helpful if we can say, if it's a measure that you and I both use, I want to say, I want to know what the probability that I'm going to randomly select a student who scores above a 60 on this quiz or evaluation or something like that. That has more meaning, right? And if we want to go directly from the raw score to the probability, that's what we need to go through, use the z-score. So we take the x value, the raw value, turn it into a z-score, and then once we've got our z-score, assuming that whatever we're looking at falls on a normal distribution, what we can do is start to pull up individual proportions there. Okay. So let's say, for this example, we got IQ scores have a normal distribution with a mean of 100, standard deviation of 15. What I want to know is the probability of randomly selecting an individual with an IQ score less than 130. All right. So Rachel, is it, just looking at this, is it going to be quite likely or very unlikely for me to randomly pull somebody with an IQ score less than 130?
It's probably pretty unlikely.
Pretty unlikely to get someone with an IQ of less than 130?
Oh, no, likely. Sorry.
Likely. There we go. Yep. I don't know what groups you run in, but
No, I was like interpreting it.
Yep. So, okay, what we've got, always want to start with, right, our distribution, right? And we know that mean is 100, standard deviation 15, And what I want to know is the probability, probability of X less than equal to 130, right? So Ari, what's the first thing I need to do to solve this? Okay, yep. So here's the mean of my distribution, and this is going to be 100, right? And I want 130, so I know I'm going to be somewhere around here. How do I know exactly where I am? What do I need to first do? What do I need to do first? Calculate a z-score.
Sorry?
Calculate my z-score here.
Okay.
Yeah. Yep. So what I'm going to do is I need to go through calculate my z, right? So I've got 130 minus, Ari, what's my mean? 100 divided by 15 gives me a z-score of what? Anybody want to help her out? 2. There we go. Perfect. Okay, so I got a z-score of 2. And I know 2 exists down here, right? With a score of 130, right? And so, Natalie, am I looking for something in the tail or in the body of this?
In the body.
Yeah. Yeah. Right, so I'm looking at all this over here, right? So what I need to do then is go to my unit normal table. I've got a z-score of 2. And Natalie, help me out. What's the probability of randomly selecting someone with an IQ score less than 130?
97.72.
Yeah, so about 97.7%. So very, very likely, right? And this comports with what I drew here. It makes sense with what I know about sort of the distribution of achievement scores. So this all looks pretty good to me. Okay. So did people follow how we went through and did that? Okay. Let's try another one.
Sorry, I actually just have one question.
Yeah, go for it.
So I just kind of get confused on whenever it's like less than or equal to compared to just less than.
Yeah.
I kind of get confused on how to,
Yeah. Functionally, right, and this gets into a little bit of theoretical math, sort of pretty basic stuff. The idea is that in this, what is the likelihood, assuming a true continuous scale, what is the likelihood of me getting an exact score of 100? It's kind of a trick question. The answer is 0. Okay? Because if I get, let's say that we're not using IQ, let's say we're looking at height, right? And height can be, I can get the precision of my measurement of height down to billionths of an inch, let's say, if my measures are precise enough. The likelihood of me having an exact, if I pull that out far enough, I'm always going to be off a little bit, right? And so when we're going through, when we talk about less than or equal or less than, you can use these interchangeably. It doesn't really matter, because what we're assuming is that the probability of finding someone, again, if we carry that measurement out to an infinite number of decimal places, of someone exactly falling on 130 is a 0 proportion. And so we can kind of use that. That's an excellent question. It gets something that's a little bit confusing, but we could say what's the probability of finding someone at or less than or equal to 130 or less than 130? It doesn't make any difference for the purposes of what we're doing here. Does that help? Does that make some sense?
Yeah.
Okay, cool. All right. So probabilities for specific values. We can also go through and start to find the probability between a couple of different values. Okay, so in this example, what we have is we've got a highway department, and they're looking at driving speeds on a local highway. Observed speed in this stretch of road, mean of 59 miles an hour, standard deviation of 10. Okay, and what we're interested in is finding the proportion or the probability of cars, the proportion of cars driving between 55 and 65 miles an hour. Okay, so Robert, what do we need to do to go through and solve this problem first?
Have to find the z-scores of both the top and the bottom, so 55 and 65.
Okay, cool. So I'm looking at something between, oops, I'll make that better, 55 to 65 miles per hour. And what's the mean in this stretch of highway that I'm finding?
9.
What is it?
59.
59. And standard deviation?
That'd be 10.
10. Okay. So one z-score, I'm going to take 55 minus 59 over 10. What's my first z-score here?
0.4.
Is it 0.4?
Oh, sorry, negative 0.4.
Negative 0.4, right? So I got 55 to 65. Okay. I get 0.40. Is that right? Negative. And then I got z of 65 minus 59 over 10. What do I get here?
That one, you get 0.6.
0.60. Okay. So, is that, I don't, you want to check your math on that? Is that right? Oh, yeah. No, you're right. I'm sorry. See, this is what I had the wrong answer here, Robert. You're the best. I'm the worst.
Get me freaking out here.
You're all right.
I gotta go back to algebra 1.
Right. Well, I guess I need to go back to algebra 1. All right. Here's my distribution, right? And this is going to be z-score of 0. This is 59 miles an hour, right? And I'm wanting to find something that goes from, let's say, negative 0.4 to 0.6. Okay? And what I'm looking for, get out of here thing, is stuff that falls in between here. Okay? So how am I going to do that? Robert, do you...
Find corresponding mean to z for each z-score, and go ahead and add those together.
Yeah. So what do I got between 0 and 0.4?
You would have 0.1554.
0.1554 plus, and 0 to 6.6? 2257. And if I add those up, what do I get?
0.3811.
Right. So the likelihood of me identifying or randomly selecting a car that's going somewhere between 55 to 65 miles an hour on this road is going to be about 38.1%, or a probability of 0.381. People see how Robert went through and was able to do that? Okay. What if we go through, let's say we want to sort of range between 65 and 75. Okay. So now, let's say we get rid of all this. Okay. Now we want 55 and what did I say? 65 and 75. 65 and 75. All right. What was my Z score for 65? 0.6. Okay. So 65 mph is Z equal 0.6. And then Z for 75 minus 59 over 10. What do we get here? 1.6. Okay. So what we need to do now, we got a normal curve. Here's 59. And Erica, where's our score, our Z score for 65 miles an hour? Above the mean, right? So we're about right here. And what about for 75? Also above the mean, so right about here. So now all of a sudden, what we've got is looking at this, okay? And so this is 0.60, and this is 1.60. How do I go through and how do I find this?
Subtract the larger portion of 1.60, as well as the larger portion of the corresponding score for 0.6.
Okay, yeah. What I can start to do is run some subtraction. So let's actually go through and let's find the proportion of the curve between the mean and 1.6. Just center to 1.6. Someone tell me what that is. 4452. Okay. And then what do I want to subtract from that? So 0.4452 is between the midpoint and here. What do I want to subtract?
Did she get that from that number, that 0.4452? I'm looking at it. Did you get that because it's the 1.60 mean to Z?
Yep.
Okay.
Yep.
So and you know the middle part. So would you just? I don't know. I'm just gonna take a stab at it. The 0.6. Would you do that again or not? Like the 0.60? Would you subtract that? Or
Yep.
not?
Subtract 0.6. Right.
Okay.
And Brittany, what is that?
It's 0.2257.
2257. Cool. Right? I take that from that. I'm going to value 0.219. There we go. Right? The likelihood of me identifying or randomly selecting a vehicle that's driving between 65 and 75 miles an hour is about 22% chance of any randomly given car driving through this area going somewhere between 65 and 75. Okay. So again, what we want to do is just get you comfortable using this unit normal table. And again, we've got here we've got mean to whatever your z-score is, larger portion, smaller portion. It's symmetrical. You can go back and forth. So just using this to start getting comfortable with working with different distributions and identifying individual scores. Okay. Here in this example, what we're doing is saying what we want to find is a minimum score to be in the top 15% of a distribution for SATs. Okay. So here, what would we want to do first, Allie?
So identify what the top 15%.
Yep. Yep. You're exactly right. So what we're going to do is what we want to do. So we want to here for this one, we want to find what score on the SAT cuts off the top 15% of the distribution. Okay. So here, what we're going to do is what we want to do is find in the larger tail or in the smaller proportion 15%, right? And if we go through, scroll down, so in the smaller portion, we're looking for 15. We get right down here to about 0.104. Okay, so what we know, we go here, we're looking for a z equal to 1.04, right? And we know we've got a mean equal to 500, standard deviation equal to 100, okay? From here, which is basic math, right? 1.04 equals x minus 500 over 100. Okay. We multiply 100, multiply by 100. We end up with 104 equals x minus 500. Oops. Add 500 here. So we get 604, right? And so we're just going through and playing with this to move around. And we can do the same thing. We can say, what's the range of values defines the middle 80% of the distribution of SAT scores? What I can do is I can just go through, find, what should I look at here in the mean to z? What proportion should I be looking for? If I want to find the middle 80%? Yep, about 40, right? So here I find z scores of, we'll say 1.28. And what I can do is then use those z scores, back translate those into scores to find sort of that middle piece of things, okay? Does anybody want me to walk through and do this, or do you kind of get the picture of how we're going through and working with this?
I'm fine with you not doing it, but I just have another question.
Yeah.
So when you look at like the top 15% or the bottom 15%, are you always looking at like the smaller proportion or larger proportion numbers? And then, is that correct?
Well, again, I can't say always, right?
But, you know,
It has to be, what we need to do again is think about what I'm actually looking at here, right? So this is where, Brittany, just plotting this out and drawing it, right? Because if I say above, below, it's all kind of relative to what I'm talking about. What I want to do is say, all right, I'm looking from here to here, and I'm looking for this, right? Or if I say below a score, it depends on whether or not the score I'm looking at is above or below the mean, right? So if I say above X score and that score is above the mean, then it's this, right? But if I want to say above X score and X score is below the mean, now it's the whole body of the table,
okay.
right?
So for the middle, so when you say like the middle 80%, what I'm trying to get at is like, is that always the mean to z, or do I need to draw it like, so the middle, I know like, so the range of values that define the middle 80%, I would just draw that and be like, oh, how do I know that I need to pick mean to z when you say middle?
Well, again, you got to go through and you want to go through and take a look, right? Because if I say the middle of, let's say, IQ scores, right?
Okay.
And I want to say scores that occur if this is 100, right? And if I say anywhere from scores from 85 to 110, right? Where's 85 fall?
Towards the left,
Below the mean. 110 above the mean. Okay, so then I'm kind of looking at that, right? What if I say I want to find scores that fall somewhere between 110 and 115? Where do both of those fall? 110 and 115. Now all of a sudden, I don't know. I can go through and decide how I want to go through and pull that out, right?
Mm-hmm.
So again, what you want to do is be able to work flexibly. Take a look at your distribution and see what portion of that space that you're looking for, and then go through and use sort of whatever makes sense. There's a lot of different ways. Robert, on that one where we were talking about traffic stuff, calculated a little bit different than I did, right? So for this, you could go through and calculate. I mean, if you said this is 1 and that's 0.5, right? You could take everything from the mean above and then calculate that out and chunk. It depends. It all kind of depends on what makes the most sense for you to chunking this out. But if you go down through and you graph it, it's going to help you identify where exactly you're looking for.
And this one would be the mean to z, like you would use that, right?
You could, yep. Or you could,
Okay.
or you could go through and you could take from 0.5 above, and then find 1 above, and it's still going to give you the same stuff, right? So there's no one way to find it. You just have to sort of whatever makes the most sense to you.
This drawing stuff is like the key to it, honestly. But yeah, okay.
Yeah. So, I told you to draw. It wasn't like I'm not going to be like later on after class. I'm like, I'm going to make those guys draw, and they don't need to. It's going to be super helpful.
Yeah, it helps a lot.
Okay. All right. So again, all this may seem a lot like trivial games, but what's important is these distributions and the corresponding probabilities. This is the foundation of our inferential statistics. Okay. What we're doing anytime we're working with a test statistic, our test statistics are associated with some known distribution with known properties. So if I'm talking about t distributions or f distributions or chi-squares, these are statistics that, assuming that we have not violated the underlying assumptions of that test statistic, is associated with a known distribution. And if I know what that distribution is, you can give me any test statistic, any value in that distribution, and I can tell you how likely it is for me to make a random observation that falls at or above or at or below whatever that cut point is. Okay? And so what starts to become important in sort of being comfortable with this is it allows us to do all the stuff that we're going to do this semester in terms of identifying probabilities for different scores. And if you understand how all this works and are comfortable with this, it's going to be much easier as you start to move forward with different analyses and interpretations, and then also troubleshooting what goes wrong, because that's the big thing, right? I think if I'm thinking about trying to get people trained up to use these, you all are in a doctoral program. Doctoral programs are research degrees. You're going to be using you're going to be practitioners of these statistical methods, right? And so sometimes things are going to go wrong. Sometimes we're going to make mistakes. What you want to know is how to go through, troubleshoot, understand, and sort of work through literature to understand consequences of violations, different types of things. So you really want to have a strong handle on this. Okay. Questions? All right. So, up to this point, what we've done is we've calculated our descriptive statistics as some estimation of our population parameters. So I'm interested in the mean height of undergraduates on the UW campus. And so what I do is I collect a sample, and I get the mean of the sample, and I say, okay, this is my best guess for that actual population parameter. I see the average height of students is 5'6", and so I say, okay, I'm guessing my best guess for the actual height of all students on campus is about 5'6". Okay, but it's important to realize anytime we're doing this stuff that our point estimates, our means, our standard deviations, these descriptive statistics that we're coming up with, these are only an approximation. Okay, our point estimate is our best guess. So again, Ari, if you go through and you're interested in the height of student undergraduates on campus, and you get a big sample, let's say you got 100 people in your sample, and average height in that sample of undergraduates is 5'6", and it looks pretty relatively representative, I'm going to say, if I ask you, Ari, so what's the average height of all students on campus? What are you going to tell me? 5, 6. Yep, and that's your best guess, right? Well, what if I pressed you? What if I said, hey, are you 100% certain that the real, actual average height of all students on campus really is 5, 6?
To my best knowledge, yes, but I couldn't tell you exactly that because I haven't sampled all of the students on campus.
Exactly, right? So we're guessing. And if you got a good sample, and if it's a big sample and it's pretty representative, 5, 6 is a pretty good guess. 5, 6 is actually a better guess than anything else that you can pull out, right? But if you pressed me and said, how certain are you? Can you guarantee me that it's the actual true value is 5'6"? I would say absolutely not, right? It's going to be somewhere in there, right? But what would be nice if we could start to add some level of precision to our estimate, like how much sort of tolerance is there? How much stuff do I have to work with? And if we could do that, that starts to become super useful. Okay, and so our solution here is interval estimates. With our interval estimation, we underutilize this in psychology and it's criminal. Our interval estimates, our confidence intervals, are going to give us both sort of our point estimate and then give us an idea of the relative precision of our whatever calculations we've made. And it's going to give us a range of plausible values for the population parameter that we're interested based on the data that we have available to us and whatever underlying assumptions are incorporated in our model. Okay, so again, all right, if I'm saying your estimate is 5'6", what would be nice is to know kind of what the tolerance is, plus or minus. Like, is it big? You'd be like, well, it's 5'6" plus or minus 12 inches, right? Is that helpful? Is that a very precise estimate? No. Does that actually tell us much of anything about the average height? No, it doesn't. It could be like, what's the average income of graduate students? Well, I don't know. It's somewhere between $0 and $3 billion. I 100% captured the actual population parameter in there, but that's not a super helpful interval, right? And so what we can start to do is it starts to give us an understanding of how much confidence we can place in sort of our estimates and sort of where they're at. Again, based on the data that we have available to us and the assumptions of the underlying model. All right, for your test of the average height of students on campus, we're assuming that you, one, have a reasonable measurement, right? That you're not just kind of eyeballing people and guesstimating, that you've actually got a valid measure. And we're also assuming that you've got a reasonably representative and random sampling of people, right? So you're just as likely to get freshmen as basketball players and other athletes and things like that in your sample, okay? So again, if we start to think about sort of the benefits of interval estimation. So we know that people, let's say we've got research suggesting that people who exercise 5 or more hours a week live longer than the average U.S. citizen, okay? Well, live longer is fine, right? But what would be more interesting is to know exactly, on average, how long do individuals who exercise 5 hours or more a week typically live, right? Because if it's 10 years, I'm going to change sort of my sedentary ways. If it's about 5 minutes, whatever, who cares, right? And sort of starting to get a sense for sort of not just is it above or below, but how much, right? Same thing if we talk about difference in heights between men and women. It's not 0, okay? That's what our statistical tests tell us. If I say men are significantly taller than women, what does that tell me? It just says that I know with sort of, I can infer with a relative degree of confidence that men and women are not the same height, right? It's just the difference is not in the populations is unlikely to be 0. Is that super interesting or relevant or informative just to say that they're not 0? Nope, it's not. What I would like to know is sort of how big is that difference? Is it big? Is it small? These are the types of things that we can start to infer with our interval estimates. Okay. So let's take a break here. We'll jump back in with interval stuff. Why don't we come back at 4:05? we'll go through, finish the rest of this, and sort of make it through our interval estimation stuff. Okay, cool. See you guys in a bit. Cool. All right, folks. Any questions before we jump into this final section on confidence interval stuff? All right, cool. Okay. I will tell you that we will spend a lot of time this semester interpreting confidence intervals, talking about confidence intervals, using confidence intervals to glean more out of our data than we would from p-value statistical tests. But confidence intervals are a thing like people really have a hard time kind of wrapping their head around this. And so what I've done is I've created an allegory for confidence intervals. It's actually not an allegory. It's just an example that's different than that. But let's say, okay, Riley, I'm going to use you as an example. Riley, where are you from originally?
Texas.
Texas. All right. Well, let's say you come to Wyoming, you get a plot of land in Texas or in Wyoming that's different from your plots of land in Texas. And I say, Riley, here's a plot of land, right? And you're wanting to know how long that land is, right? We don't know because we don't have something to actually go through and sort of measure this out. But in actual fact, this plot of land is exactly 100 yards. Okay, and so well, damn it. Let's say it's 100 feet. It's a small plot of land. It's more a garden than a plot of land. Let's pretend it's 100 feet. But you don't have any information, but you can step this off, right? So you decide to step this off. You go through, take a look on the internet, and you see the average stride of an average person is about 5 feet, I guess is what it told me. You step off this track, you get 19 paces, suggests it's 95 feet. Okay. So if I ask you, how big of this is this garden that I just gave you, what are you going to say? 95 feet. But you probably realize that that's not a precise estimate, right? You're like, it's 95 feet-ish, right? That's kind of my best guess. It's a good guess. It's not perfect, though. If I have Erica go through, step it off, Erica's probably going to come up with a slightly different number, right? If you go through and you walk it off again, you might get a slightly different number, right? And so because you realize that you've made this measurement with some error, if I say, Riley, how long is this piece of land? You're going to say 95 feet. I say, could it be 96 feet? You'd probably say 96 feet. Sure, could be 96. What about 98? Could be 98 feet? Fair enough, right? Say 105. It's starting to get maybe a little bit. You're like, it's starting to get off, right? At some point, though, I'm going to get to a point where you're like, no, it's probably not. At least based on the data that I've collected, that doesn't seem like a reasonable guess based on what we've got here. Okay, so what you've done in this scenario is you've kind of put together an informal confidence interval with this. Okay, you have some unknown quantity, right? And you have an imprecise measurement. You've gone through and made your best guess, but you know it's not perfect. Okay, if I ask you if it could be this, if it's something close to your estimate, you say, sure, it could be that. Is it your favorite estimate? No, your favorite estimate is the one you actually made, but fair enough, it could be around here, right? But if we start to get too far below or too far above, you're going to say, well, I don't know. Is it impossible for it to be sort of X length? No. Is that consistent with the data that I've collected? No. So I'm going to say that's like that is a guess, but it's not falling within what I think is going to be a likely value. Okay, and this is essentially what we're doing with our confidence intervals. We're saying this is my best guess at some population parameter of interest, but it's a fallible guess, and it's based on sort of the sample I could get. Based on my data, here's my best guess. Here's a reasonable upper limit. Here's a reasonable lower limit. My point estimate is still my best guess, but we would say the data would reasonably support anything between these two maybe limits. And if it does, if I give a guess in the middle, you're going to say, sure, fair enough. Okay. But when we're thinking about our confidence intervals, again, what's important to realize is that any interval that we calculate over the course of this class is just one interval of some infinite number of intervals that could be drawn from replication, right? If we had everybody in class and all the faculty, all of psychology walk this plot of land, they're all going to get slightly different estimates, right? And my estimate is probably going to be quite a bit different than, say, Robin's estimate, because I'm quite a bit taller than Robin is, right? And so we're going to have different leveling precision. And some people's intervals are going to be a little bit wider. Some people's are going to be a little bit narrow. Some people's intervals might not even capture their actual value, right? And so if we're thinking about confidence intervals, right? And again, let's go back to Ari. This is people drawing intervals of average height for students on UW campus. If we keep doing this, if Ari generated a sample of 50 individuals, and it's a true random sample, but if we keep doing this over and over and over and over and over again, we're going to get a lot of different intervals. Now, hopefully, most of those intervals are going to be kind of in the same range, right? The guess that I proposed to Erica and her interval should be probably, hopefully, pretty reasonable to Rachel and her interval, right? But for any one individual, any interval, we don't know whether or not that interval actually contains whatever population value we're trying to get. If we take a look at these intervals here, this is the actual population value here, 0 or 50, right? And most of these are capturing that, right? But we've got some intervals, 1, 2, 3, where that doesn't capture the population value, right? Now, Allie, if this is Allie's interval, Allie and I say, hey, is 50 a reasonable score for whatever it is we're estimating in terms of population value? What are you going to say?
Sorry, what was the question?
So this is your interval here. Okay, you see it? Sort of going from here to here. Okay, if I ask you if 50 is a reasonable guess for the true population value, what are you going to tell me? You would say no, right? But if you conducted this study in isolation without seeing any of this, right, no is a reasonable answer. Based on the data that you've collected, 50 isn't a reasonable guess for whatever it is that we're measuring here. Now, the actual value is 50, and all these other studies found 50, but in the absence of just one, like, you don't know, right? So some of these intervals are not going to contain the true value. Some of them are. But this is the idea behind meta-analyses, is what we go through is we try and aggregate lots and lots of studies and start to take a look to see sort of what are the data starting to converge on some estimate of the actual population value. That average is going to give us a much better and more accurate estimate than any one of these individual studies in isolation. Okay, so people kind of seeing getting the idea of these confidence intervals, what we're trying to do, and sort of how we're trying to use this to model some level of imprecision in our estimates. Questions? Okay. So if we're talking about the calculation of confidence intervals as a statistical tool, confidence interval is an interval estimate based on some assumed level of precision. Components of my confidence interval are going to be my point estimate. This is my best guess. Push comes to shove. This is the guess I'm going down to the mat with here. Okay. But what I do is I choose a level of estimation, and then I create an interval based on that level of estimation, right? So Allie, if you say, hey, you tell me, you make a bet, you have to bet everything you own on some estimate of this population parameter, what's my best guess going to be given this interval here?
That it's going to be between 18 and 43.
Oh, see, but you're not letting me do that. That's cheating. You say one number. What am I going to guess?
Oh, the 30.5.
30.5, right? But based on my level of precision, I would say any guess falling between 18 and 43 is reasonable. We would say that would be supported by the interval that I've collected here, right? So we've got a point estimate, we've got a level of estimation, and then we've got our upper and our lower bounds, okay? And so when we're talking about interpreting these, This is the formal interpretation. I want you to know this, but I never want you to use it when you're actually trying to explain it, because this is egghead math stuff that won't make sense to the average person. Okay? Formal interpretation of a confidence interval, I would say over an infinite number of replications, my confidence, the procedure for getting my confidence intervals, or that level of estimation, is the proportion of intervals expected to capture my true population value. Okay, so here when we're looking at, R is looking at average height of University of Wyoming students. Over an infinite number of samples with replication of size 100, I would say if my level of precision, if RA chooses their level of precision at 95%, I would say 95% of the actual intervals that are calculated will actually capture the true population. The other 5% are going to be these folks hanging out, right? There's nothing wrong with these estimates in their construction. They just happen to not capture the population of interest, or the parameter of interest. Okay. So what I want to convey here is that our confidence in the confidence interval, think about this as a level of estimation, it's a property of the method, not of any one actual specific individual interval. Okay. So what will happen a lot of times is people will say there's a 95% chance that the confidence interval contains the actual population parameter. This is incorrect from a conceptual technical level, because that's not what the interval is saying. The interval is saying, if I were to replicate this study 100 times, 95% of the intervals that I would generate would cover the actual population parameter. What this doesn't tell me is whether or not any one individual confidence interval that I've calculated, or the calculation or the interval that I'm looking at right now, actually contains whatever parameter that I'm interested in. Okay. And the reason behind this, want people to have a very, very good understanding. So, because this is like, you'll see this in text, and people will always do this. There's a 95% chance that the population parameter falls within sort of X and Y. Incorrect. Because what are confidence intervals? It takes a frequentist approach, right? It assumes that if I go through and I continue to draw samples from a hypothetical population, each one of those replications is going to have its own interval. Okay, and sometimes, well, always, these individual intervals will vary, and sometimes they're going to vary by quite a bit. Some of our intervals are going to capture our population estimate, or our parameter of interest. Some of them aren't. This is where that level of estimation comes in, right? If I say again, if I'm saying, I can tell you with 100% confidence that the average income of graduate students is somewhere between $0 and $3 million a year. Okay, but that's a super wide interval estimate. That actually doesn't contain, that's cheating, right? That's not useful information. As we start to sort of increase our level of precision, what we do is we start to get more and more of our intervals that aren't going to actually go through and capture the population parameter. But what we do for any individual study, if we don't know anything else, we could be one of these intervals, right? And we've completely missed, our upper or lower bound has completely missed that true population parameter, but we don't know it if we're just looking at that one in isolation. Okay. And so what happens if I claim that there's a 95% chance that my interval, right, the one that I've collected, actually contains the true population value? That implies that my population parameter is a variable. Okay. So if let's say I've calculated a confidence interval, and so my point estimate is 100, and I say the upper and lower limits of my confidence interval are anywhere between 90 and 110. And I say there's a 95% chance that the true population parameter falls between 90 and 110. Okay, that's suggesting that sometimes the population parameter is going to be between 90 and 110. Sometimes the parameter is not going to be between 90 and 110, suggesting that population parameter sort of jumps around. Population parameter is the population parameter. The likelihood of the population parameter falling between, well, let's say 3.45 and 7.86, it's either 0 or 100, right? Either the population parameter falls in there or it doesn't, right? There's no variability going on here. And so when we start saying there's a 95% chance that my interval contains the actual population parameter, it's misrepresented what I'm actually looking for. What's variable is my intervals, right? The population parameter is some number. It's unknowable, but it's some hypothetical number out there, and either my interval captures it or it doesn't. If I've got a 95%, if I'm calculating 95% confidence intervals, 95% of the intervals that I could hypothetically generate from this a sample of a certain size, 95% of them are expected to capture that population parameter, 5% aren't. If I go a 90% confidence interval, I'm saying that 90% of these intervals are going to capture, 10% aren't. If I 99% interval, right, what I'm saying is 99% of the all possible intervals that I could collect of a given sample of a given size will capture, but 1% aren't, right? So just thinking about this, what happens to my interval as my level of estimation gets larger, higher and higher? So what's the difference, Ali, between a confidence interval? If I have a 99% confidence interval versus a 95% confidence interval, which one of those confidence intervals is wider?
The 99%.
The 99, because it's a bigger thing. 99% of my intervals are going to capture the population parameter because my intervals are wider, right? My 100% confidence interval for the average income of graduate students ranging from $0 to $1 million, it's massive, right? So it's sort of shotgun approach. As I start to sort of go down, then I start to get sort of more and more precise measures, but I miss the population parameter more often, okay? And so, quote from Neiman sort of captures this. Sort of coverage probability is a property of the log sequence of intervals computed from valid models, as opposed to the property of any single individual on its own. Okay, so when we're talking about the level of estimation, it's a property of the process, not your individual confidence interval. Okay, and so what we want to think about are your confidence interval that you go through and calculate. This is a best case scenario. Like anything that we do in this class, the validity of any of the measurements that we create or any of the statistics we run are assuming that I've got a representative sample, that my data are playing according to all the the assumptions of my tests, that I haven't made any big violations that are going through and throw things off. It all starts to become very contingent. So to the extent to which my inferences and my conclusions are valid are only as good as the level of data and methodology that I've collected. Okay. So this is super important. Do people understand why it's technically incorrect if I say 95%? There's a 95% chance that sort of my estimate of 3.45 to 7.86 contains sort of my actual population parameter. You getting this? Okay. So our actual sort of technical interpretation, formal interpretation, over an infinite number of replications, the proportion of intervals expected to capture the true population value. But if you're talking to your grandma probably doesn't understand, unless she's sort of a scientist or sort of works with statistics, what an infinite number of replications are, right? So if we're trying to provide conceptual interpretations that are consistent with what we're actually doing, that actually means something to people, a number of different ways we might go through and talk about this. We could say that a confidence interval represents a range of plausible values for some parameter given the available data. So based on the data that I have, my interval represents sort of values that are plausible. Okay, values falling outside the interval, relatively implausible, given the data and the underlying model. So I have to sort of make sure that whatever model I've used to calculate this is valid. Okay, that means that values falling outside of my intervals, outside my upper lower limit, they're not probable based on my model and the data that I've collected, but it's not impossible. They definitely could fall there. Okay, so we like that one. We could also describe our confidence interval as saying our observed data are compatible with values of whatever parameter I'm looking for falling within this interval, relatively incompatible with values falling outside the interval. Okay, so here's guesses that are kind of consistent with what we found. Here's our guesses that are going to be inconsistent. We like that one. Say values are compatible with these interval gives me values that are compatible with the data given the underlying model, ranging from my lower limit to my upper limit. Makes some sense. I like this. I can say lower limit provides a plausible lower bound estimate for the parameter. The upper limit is a reasonable upper bound based on the data that I've got. Okay. We like this. We could say the margin of error, that's sort of the plus or minus my point estimate, is the largest error of expected error of estimation based on the data in the underlying model, right? So this is going to say if I've got, so if I say my best guess is 100 and I've got an upper limit of 110, a lower limit of 90, I would say this margin of error of about 10 points is the largest expected error of estimation based on the data. We like that. We can be 95% confident that our interval includes the parameter of interest. We don't like that. I don't like that at all. Don't write that. Use one of these things here because this is what we are saying is not consistent with sort of what's actually being provided by these interval estimates. Okay. So what I'm going to do, like sort of take this slide, circle it in whatever electronic sort of way. This is sort of the way I would, I'm trying to give you words for ways to think about and conceptualize and communicate what's going on with our interval estimates. Okay. Change it up, use different things, sort of try and think about this in a way, because what we will do with these is try and think clearly and carefully about what our data are telling us and the types of inferences that we can go through and make. Okay. All right. Oh, Cohen. So a researcher routinely reports 95% confidence intervals can expect it over a lifetime. About 95% of the intervals will capture the parameters estimated. Right? I mean, also a nice way to think about this, right? 95% of the time, I'll have something that captures it. The other 5% of the time, I won't. Do I know when I will or when I don't capture the population parameter? I don't know. Right? So it's a probability estimate. It's a characteristic of the process, not about any given interval. Okay. So this is a lot of stuff, right? And so people are like, we know that interval estimation is good, and people will say, oh yeah, it's a better way to do things than straight up hypothesis testing, sort of p-values, yes, no dichotomous decisions, right? But why is it better, right? Some things to think about. Our interval estimates are going to give us both a point estimate, right? Sort of whatever we think our population parameter is, and it's also going to give us an estimate of our expected precision of whatever it is I'm trying to think about. So what we get with our interval estimate tells us not just, or it's giving us an emphasis of how much, as opposed to just is this zero, okay? And sort of this, you think about the width of your confidence interval as an index of the precision of your estimates. Okay, so I'm going to pick on clinical folks. So let's say Natalie, you're looking at so your research interest is sexual assault prevention. Is that right? Okay, so you run a study, right? And you say that you find and you use traditional methods. And you say that your intervention has a significant impact on rates of sexual assault on college campuses. Are you excited about that?
A significant impact, you said?
Yeah.
Yes, I guess so.
Yeah, you guess so, right? Because significant sounds important, right? What does significant mean in a hypothesis test?
Means the p-value is less than 0.05.
Means it's less than 0.05, right? And what it technically means is just something isn't zero, right? What it says is that your intervention, based on the data that we've collected, that the impact of your intervention on rates of sexual assault at college campuses is not zero, okay? Now, if you put your clinical hat on is not zero something that's a useful or informative way to think about sort of impacts? No, it's actually not, right? Particularly if you've got an intervention that's very, very complex, very, very expensive, right? And so if I say my intervention or my manipulation or anything has a significant effect, it just means that it's the data suggests that it's not zero, right? What I might want to know instead is to say that my intervention creates a, let's say, 15% reduction in rates of sexual assault on campus. Are you excited about that? I'd be super excited about that, right? So, okay. But what if I then said, okay, so then you go through and you create a confidence interval around that, and you say based on our data and the model that we've used, we've got a 15% reduction, and my 95% confidence interval for that ranges anywhere from a 0.1%, a tenth of a percent reduction to a 30% reduction. What happened to your sort of feelings about the effect that you've had there?
Seems way less exciting.
Way less exciting. Why is that?
Because it's possible that it could be a tenth of a percent.
Exactly.
Which is
Right. Does that mean you shouldn't be excited about your study or sort of think that it could be helpful?
not necessarily. You just need more specific data to explain it.
Exactly, right? Because again, what's your best estimate based on the data that you've collected for the true impact of your program? 15%, and that's pretty good, particularly for what you're trying to do, right? But what it should start to do is start to sort of put into context that estimate, right? So what you're saying is this could be 15% is pretty good, but it could be anywhere from functionally zero to something that's really massive. I just don't know. And that's a much better place to be than saying that my treatment has a non-zero impact on something. Okay, there's just much more information in here. And would we suggest, based in this scenario, that you have a very precise estimate or a very imprecise estimate?
Imprecise because it's very.
Yeah, it's pretty imprecise, right? So if I was reviewing your study, I would say, okay, this maybe looks promising, right? But if in your discussion section you're telling me how this is going to revolutionize everything and how you have conclusive evidence of massive impacts, and this is better than anything that's ever been out there before, I might start to sort of take some exception to what you've interpreted from these data, because what I've seen here is this estimate, or the sort of the imprecision in your estimates, okay? And so what we want to do is just use these to try and get a good handle on sort of where we're at in terms of our estimates. Our interval estimates also help us start to give more accurate and meaningful comparisons relative to stuff that's observed in the existing literature, right? So Rachel, let's say that you find a study and you say you find a difference between group A and group B of 15 points, right? And you look, and Erica's got a study looking at the same type of methodology, the same thing, and she's got found a difference of 25 points, right? Is that is your study comparable to Erica's, or is it not comparable to Erica's?
Okay, I'm a little confused about what you're asking.
Okay.
So I have 15.
Uh-huh.
Erica has 25.
Yeah.
Are they the exact same study?
Yep, same thing. Same study, same sort of just general method, population, things like that. Can we tell if they're comparable?
Not really.
Not really, right? I don't know, right? It depends on the precision of your estimates and the precision of Erica's estimates, right? Now, if you're, say, 15 plus or minus 10, and Erica has 25 plus or minus 15, there's a lot of overlap in that, right? And so we would say that your stuff is actually, even though you found a smaller effect than Erica did, we'd say in general, it's kind of looking like it's the same thing, right? If you're 15 plus or minus 3 and Erica's 25 plus or minus 5, now we're in a different situation, right? So our interval estimates can start to help us sort of go through and compare where our effects are relative to the larger literature. Okay. Our interval estimates also give us a much, much better assessment of the extent to which, again, sort of comparability in terms of, well, I guess this is what I jumped into sort of right away, but then also thinking about sort of where our estimates fall relative to null values or reasonable values, right? If I'm doing some study and I say, in order to make this manipulation work, it has to be a certain amount, a degree of increase or decrease based on something, right? And if I have a upper or lower bound that's very, very close to whatever value would be functionally meaningless, I start to have less confidence in that being a sort of a reasonable manipulation or treatment relative to something where my lower bound is maybe quite a ways across what would be a functional sort of meaningless result for me. Okay, so again, with our interval estimates, what this is doing is giving us, based our best guess, plus or minus a tolerance, right? But what the advantage that this has above just our straight statistical tests is our statistical test will tell us, do we have evidence that it's probably different than zero? Let's say sure or not sure, right? Our interval estimates tell us about how much. Okay. So again, from that Wilkinson article, we've been talking about this a lot before, about sort of why confidence intervals are effective, why they're useful, why they contain much more information. We still don't use them appropriately in our field. I think a lot of that is because of training and exposure and use. And so against your will, perhaps, we will spend all of this semester thinking about things in terms of interval estimates, in addition to sort of our statistical tests. We'll use those, right? Does anybody have a problem identifying something that's greater or less than 0.05? Thumbs up if everybody got a handle on that. Cool. So you can identify things as significant, not significant if you want, right? But what we're going to do is focus sort of on more nuanced interpretation based on our interval estimates. Yeah. So additional things that we want to think about in terms of our confidence intervals. Practical upper and lower bounds for our estimates, okay? I'll use clinical as an example just because it's sort of a helpful type of thing, right? Or just because it's an easy example. If I have a treatment for PTSD, right, and given the time and effort and everything else that's out there, I'm going to say, unless my intervention creates a 15-point reduction in symptoms, it's not worth the time or the cost or effort or anything else that's out there already, right? And so if I run a study and I find that I have a significant effect of my treatment, that significant effect just says that symptom reductions are likely not zero. Likely not zero is not a useful thing for me, right? What I can do is I can calculate an interval estimate for that change and say, look at the lower bound. So my data say I've gotten a 20-point reduction, but anything from 16 to 24 is reasonable estimate given the data that I've collected. Well, my lower bound suggests a reduction, sort of at minimum a reduction of 14. If I say I need 10 at most, or at most in order to make this helpful, I feel like I'm doing pretty good, right? But if I say I need to have at least a 10-point reduction and my lower bound is 5, right? My point estimate is maybe sort of higher than sort of, let's say my point estimate is 15, my lower bound, or my point estimate is 15, my lower bound is 5, I need 10, I'm kind of in there, but my results are kind of ambiguous, right? So what we want to do when we're thinking about this as thinking about even if my results are actually indicating consistent with the lower bound estimate, what can I determine from that? Is it still useful? Is it not useful? What does this do for my interpretations? Okay. Also, if I have a very wide interval, right? If the impact of my treatment is anywhere from a 2-point reduction to a 30-point reduction, is that a useful study? Does it tell me anything meaningful about my treatment? Well, it suggests that I might move the needle a little bit, but really super, super ambiguous on whether or not I've actually sort of done or demonstrated anything that has any sort of practical use. So thinking about what are the practical implications of this upper and lower bound, and how does that help me inform my evaluation of my research? Okay. Also important to remember that our interval estimates, any of our statistics, are only as good as my methods, my underlying models. Okay. Our confidence intervals, we're basing these on mathematical ideals, but my interval estimates are also associated with a great deal of error, and are going to jump around from replication to replication. I'm not going to get the same interval each time, right? And even my upper and lower bound estimates are still going to be associated with error, right? This is the thing we go through and we say, if my lower bound estimate doesn't contain my null value, if my lower bound estimate doesn't contain 0, that's, in hypothesis testing, would be consistent with a significant effect, right? But if my lower bound estimate is 0.1 and my null value is 0, functionally 0 is still a reasonable guess for where I'm at with stuff, right? So I'm wanting to think carefully there. Other thing we need to think about is that we can't just look at statistics, confidence intervals or otherwise, in the absence of evaluating the methods, right? What's my recruitment look like? What's my sampling strategy? What are the measures that I've used? What are my experimental procedures that I've included? What choices have I made in terms of analyses? Have I violated underlying assumptions of my models? All of this stuff starts to become important. Also thinking about existing evidence, right? If I've got, Rachel, you've got a study that's found effect. Basically every published study has found a relationship between X and Y, right? And then you run a study and you find that X isn't related to Y. Does that mean that your data has disconfirmed an entire literature?
No.
Nope. What's maybe a better guess for what's gone on?
Something to do with your sample.
Could be something to do with my sample. I would want to think carefully about what have I done that's maybe different than other people that made me miss this. Or, this is the other thing too, you could have run a perfect study. Your study could have been exactly, you could have done everything right? But sometimes we're going to have studies that fall on the tails, that just miss it just because, right? Your study could be that too, right? But we see this all the time, right? We see one study say, oh, this is an effect or this is not an effect. You can't evaluate that absent the larger literature. Your one study doesn't trump everybody else's stuff if there's a consistent effect, right? So we need to be thinking about that, right? And so again, remembering that our point estimates are going to jump around. Our intervals are going to sort of change sizes. Different studies are going to have different estimates. What we want to do is remember to stay flexible with this and not sort of get stuck on hard and fast rules to say this is or isn't a thing, or sort of if it falls sort of below this bright line that it's not a thing, but if it does, it's above. Want to keep flexible as we're going through and thinking about this and sort of incorporating both our statistics and our figures and our methods and bringing these together to try and pull together some reasonable interpretations about whatever phenomena it is that we're looking at. Okay. Questions about this? All right. Again, going to be asking you to you're going to interpret so many confidence intervals. I'm going to be watching you. I'm going to be making sure you're thinking about this stuff and sort of going through. Honestly, the amount of points that people lose for not interpreting confidence intervals, it's a big chunk of points, right? Like you want to be I want your entire thought process to be oriented about thinking, what's the upper value? What's the lower value? You're going to be looking for this in your assignment. So when we get to this point, so just making sure that you're thinking carefully about this and filling this stuff out. Okay. Last year, I was like, I can't find, there's like nowhere on the internet is a picture of Sting in a police outfit. And then like Chris Mancuso, he was supposed to be paying attention while I was talking about, but instead he was Googling Sting in a police. He found it like 3 seconds. So this is courtesy because Chris found it. He didn't take the shot. That would be a cooler story, but that's not what happened. But okay. So calculating confidence intervals. Okay, 3 pieces of information with our with our confidence intervals, at least for means-based stuff. We've got our sample mean, we've got a standard error, and then our Z or T value sort of for our chosen level of estimation. One thing we want to touch base on quickly here, we'll talk about this later on, talking about our standard error. Know and love standard error. If you're ever at a loss for an answer, standard error is statistically a good guess in this class. Wanting to have a good understanding of what standard error is, think about standard error as an index of how much of a sort of a jump or how much variability or how much of a difference is expected from one sample to the next. Okay. Our standard error gives us a measure of how well an individual sample is expected to estimate the actual population mean. Okay, and so if I say I've measured something with a mean of 100 and my standard error is 5, what that means is that if I were to go through and repeat this study time and time and time and time and time again, an infinite number of times, an infinite number of replications drawn from the same sample with a sample of the same size, I would expect that on average, that my point estimate of 100 is going to jump around by about plus or minus 5 points across an infinite number of replications. Okay, so Allie, do we like large standard errors or small standard errors?
Small ones.
Small standard errors. That means that based on the data that I've collected, I'm expecting estimates in terms of replications to jump around much less than if I have larger estimates. Okay. If we go through and we take a look at our standard error, easy to calculate for standard error of the mean. It's just going to be our standard deviation divided by the square root of our sample size. So I take whatever my measure of variability is, my standard deviation, divided by the sample size, that's going to give me my standard error. Okay. So what happens, Erica, what are my primary influences on standard error, just based on this equation here? Sample size and standard deviation. And what's the thing that's really going to impact my standard error based on this formula? My sample size. And what happens as my sample size increases? What happens to my standard error? It decreases. It starts to get small, right? So if I'm running samples of, and if we think about what standard error is telling us, if you're measuring, some construct in samples of size 20, how much are you expecting that mean value to jump around across individual studies or individual replications? Quite a bit, right? What if you got a sample size of 500? How much are you expecting that mean to shift around? Not a lot. It's going to stay pretty consistent, right? And Erica, can you tell us, why does this make sense given what we know about sampling and sample size and things along those lines?
You're more likely to capture the population, or you have more of the population, so you're more likely to capture the population parameter.
Yeah, I'm getting much closer, right? I'm getting a much better estimate with a sample of 500 than I am of 20, right? I'm getting more of the population, assuming it's a good sample. I've got more people in there. I've got a much more stable estimate of that actual parameter than if I have a sample of 20. Sample of 20, I can jump all over the place, right? This is one of the big things in psychology research where we get all worked up about our replication crisis. Well, of course we have, right? Because we're oftentimes working with very small samples, particularly in historical research, and it jumps around all over the place. If I'm working with sample sizes at 15 and 20, I'm going to be all over the board, right? But as I start to get larger and larger samples, if I get samples 100, 200, 300, now all of a sudden, so that I'm going to be very consistent in terms of where I'm at in terms of my estimates, okay? So just be thinking about that in terms of our standard errors, the influences going in, and how this is all coming together. Okay, so again, want to make sure that you're feeling good about this. For the confidence intervals that we're going to go through and calculate, so we've got our mean, our standard error, and then our Z value for a chosen level of estimation. 90% confidence interval is associated with a Z value of 1.65, 95% confidence interval 1.96, 99% 2.58, okay? And anybody tell me where these numbers are coming from? This is just going to be my Z table, right? If I go down through, so my 95% confidence interval associated with a Z value of 1.96. If I go here, right, what percentage RA is in the upper tail at for a Z value of 1.96? Yeah, for Z value of 1.96, what percentage of the distribution is in the upper tail? 2.5%, right? And what's going to be in the lower tail at negative 1.96? Well, if we're looking at bounds between negative 0.196 and positive 0.196, what's the percentage going to be in each tail? Yeah. So if I'm looking at a value of 1.96, negative 1.96, what am I going to find in the tails here? So remember this is symmetrical, right? So if I've got 2.5% in the upper tail, what am I going to find in the lower tail? 2.5, right? I add those together, that's 5%. This is getting my 95% confidence interval, okay? Same thing if I go through, if I take a look at 99% confidence interval, 2.58%, right? If I go down to Z-score 2.58, I've got about 5% in the upper tail, 5% in the lower, or a 0.5% in the upper tail, 0.5% in the lower tail. That's 99% sort of that I've captured there. So this is where these are coming from. These are just good numbers, just kind of have memorized for different confidence intervals. Okay. So my formula is for my confidence interval is just going to be, if I'm calculating confidence intervals around the mean, it's going to be my mean value plus or minus my Z-score for my level of estimation multiplied by my standard error. Okay. And so if I do that, I'm going to go through, I'm going to get my confidence intervals, and then I can go through and make sort of interpretations from there. All right. We've got a couple of examples here. I don't want to jump into those. We'll do those next time. But one thing to think about in terms of, to finish up, in terms of thinking about your interval estimates. Who I not picked on for a while? Where'd Robert go? There's Robert. Okay. Robert, we can think about my confidence bound here, right? I have a point estimate here, and here's my lower and my upper bound for my confidence interval. We can think about the probability of the population value not being uniform across this interval, okay? If we're looking at this, we can think about this as kind of having sort of a distribution, and my confidence bounds kind of fall within here. So for this interval here, where's my best guess? What's my most likely guess for the actual value of a population parameter?
I guess I'm confused by the question.
Okay, so I've run a confidence interval. Right here is my mean value. So it looks like a little under 24. My confidence bound says that any value from a little over 25 to, say, 22.5 would be supported or reasonable given the data that I've collected, right? Does that mean that any value from 22.5 to a little over 25 are all equally likely? No. Where's my best guess? Yeah, my mean. My mean's always going to be my best guess, right? So in my example where, going back to my example where Riley's stepping off her plot of garden land that she's been awarded because she moved to Wyoming, right? It snows in September, so watch out for that. Growing season is short. If she says it's 95 feet, and that's her guess, right? And we say, oh, what about 96? What about 97? What about 100, right? Even if those are in her interval estimate, Riley, where's still your best guess going to be? 95, right? And so as we start to get farther and farther out, what we see is our guesses, sort of our supported values, become less and less supported and less plausible, right? They're not impossible, but we've got a nice distribution even within that interval estimate. And this is what sometimes people get confused by. They'll say, well, it was in the confidence interval, so it's equally likely as anything else. But no, it's actually not. Our best guess is still always going to be our point estimate, whatever our parameter is that we guess, right? Because remember, our mean is an unbiased estimate of the population parameter. So our mean is still going to be the best guess. But given the level of precision of our data and our study and everything else, we're saying that anything from here to here is at least supported or at least plausible given the data, but it's not all equally likely, okay? And so wanting to think about this as we're going through and making our interpretations of our interval estimates. People kind of see what's going on with these graphs. Does this make some sense as you're thinking about what confidence intervals are, how we go through and play around and interpret with these? All right. We'll finish up on next Wednesday with a couple of different examples. So to go through, give you some language to go through, start thinking about kind of what's going on with this. Any questions on this? Big questions on the stuff that we've covered up to this point? Okay. So here's what's going to happen. So you've got a problem set that's due on Friday. Okay. So make sure that you've gone through, taken a look at that you've looked carefully at all your answers, that you've kind of got those fleshed out. Make sure that you have an appendix attached to that. And again, it's just literally you just say number 4, mean is whatever, standard deviation is whatever, and just having the numbers there. That'll go through, help us streamline our checks. So go through and do that. Now on the syllabus, it says that we were supposed to finish confidence interval stuff today, and then you would have a problem set due sort of next Friday. That's not going to happen because we haven't sort of gone through all that stuff yet. What I'll do is I'll post that. Now don't get worked up because then you'll have 2 problem sets in your box while you're still working on one. I just want to get that out to you so you can start taking a look at that whenever you want. This next set, problem set 2, won't be due next Friday. It will be due the following Friday because we'll get done with stuff next week. So don't get too worked up about that. As you're making this last push, if you have any questions, make sure to get in touch with CJ or I. Anything else that I'm forgetting?
So just to clarify, the next problem set will be due on the 25th, just to make sure I have the dates.
Let me see. Yeah. So, yep, we'll be on the 25th is when that'll be due. So, again, this next set also will be sort of pretty straightforward application. Just wanting to give you some mileage in interpreting confidence intervals and things like that. I don't know, CJ, any thoughts, words of wisdom, things that helped you as you were trying to wrap your head around confidence intervals, trying to think about these things carefully?
Specific, but just referring to the slides especially helped a lot because this is something you've gone over before, then it's easy to kind of mess up that definition, I guess. So yeah, look back at the slides at those various ways of explaining that.
Yeah. And so when we get to this point, what I would love to see, and will actually give you extra points if I do see this, is people starting to be flexible in their interpretations. I think the knee-jerk reaction is to have my cut and paste interpretation of confidence intervals. And technically you won't be wrong sometimes, but if you're just cutting and pasting, you'll screw stuff up and it'll be wrong and I'll flag it. what you want to be able to do, like anything else, the more ways I can talk about this and explain this and express this, the better it is that you'll understand it and be able to use it well. And so I think this is the trap people fall into sometimes with statistical models. Back, oh, what are the correct words that I need to use to describe this? Well, you need to have, I mean, your words need to be correct. But if I can explain it in a couple of different ways, it tells me that you sort of understand it, know it, can use it flexibly, because the way you describe something for one problem might not be the best way to describe it for another problem. And so just want to think about using this flexibly. Okay. And if we do this now, you're going to be, and if you get sort of a handle on this early, it'll help you out in the long run, because otherwise you won't keep making the same mistakes over and over again on these assignments. Okay. Cool. All right, folks. 3 hours of stat via Zoom is always a slog. It's exciting for me. I always like to see you guys. It's the best part of my week to talk about numbers for 3 hours. I can see Natalie's excited about it too. It's like the emoji, like, that's weird. That's just straight teeth. That's what Tara sends to people to say that she's smiling, but it's confusing. I beg, like, you're sending people grimaces. Like, that looks like a grimace, and it's sending mixed messages to people. But cool. All right. Thanks for hanging in there. I'll get this downloaded up to Wild Courses, and again, just click that link for the video archive. It'll sort of take you all this stuff. Okay. All right, folks. We'll see you later. Have a good week. Let me know if you have run into any difficulties. Cool. All right. We'll see you.